this video, we are starting with relational set operators. Like the relational set operations, we do have some set of operators which we can implement on the relational databases or tables. So see, for understanding all the operations of the operators, here in this video we are going to use the customer table and the agent table. Just try to review this. The customer table has 4 columns and the agent table has 2 columns. So using this, first we are going to learn about a type of join called natural join. So actually this join is processed in 3 steps or 3 stages. The first one is to find out the product of the 2 tables that I have just shown you in previous figure. Um, and using those 2 tables we are going to perform our natural join. So the natural join, actually what it does, it links the tables, those 2 tables, by selecting only the rows with common values in their common attribute. So what are the common attributes? Agent code in both the tables. So if you see customer agent code and this is your agent code, based on that the merging or the join is performed. So based on the similar value of this customer agent code and agent code, the first operation is performed. This is your first step, which is nothing but the product operation that we have already seen earlier. Then second step 2, next in that product operation result, whatever we got, second a select is performed on the output of step 1, the last step, to yield only the rows for which the agent code values are equal. So here we are trying to link the tables by selecting only the rows with common values in their common attribute. So any common value, first it will try to compare with the customer agent code and agent code, and wherever there is a common value, that common value with its associated whole record, all the attribute values, all of them will be included in the resultant select second step of natural join. Next comes the last step, which is project. So from the step 2, here a project operation is performed to have only resulting agent code column. Rather than having 2 agent code columns from customer and agent, we are trying to just project 1 agent code and the associated values of other columns as well. So this is your natural join, which is performed through 3 steps. Next, let's see the Equi Join. So the Equi Join actually performed the way in which it links the tables on the basis of an equality condition that compares specified columns of each table. So we are still using the same table, agent table and customer table. Okay. So based on the the project operation that you had or the select operation that you had in the natural join, we are going to use the second step here. Okay. And this is nothing but your Equi join. Next comes the inner join. So in the inner join, we have customers table and orders table. Here in this join, it only returns the matched records from the tables that are being joined. So matched record and how it will be performed then. See, we have ID common to both of the table, right? So based on the matched record of both the tables, mostly based on the ID values, the 2 tables will be joined together. So wherever there is a matching ID value of both the tables, customers and orders, that corresponding row will be selected in the resulting table. ID, name, amount and date. Next comes outer join. So outer join, actually what happens here? Here matched pairs are retained and unmatched values in the other table are left null. So first we will see the left outer join. So in the left outer join, actually what happens, it yields all the rows of the first table, left outer, everything, matching, non-matching record. All of them will be included, including those that do not have matching value in the second table as well. So that, see, if you see starting with the first row, so there is a matching agent code value of customer agent, but there is one extra record from the customer table for which a matching agent code is not being found. So this is what the left outer join looks like. So left side relation must not be kept empty while the right side can be empty. And just the opposite of it is the right outer join, which yields all the rows in the second table, including those that do not have a matching value of the first table. Okay, so see the empty values are now in the left hand table. Next is divide. So this is a type of operation divide in which we have two tables, table 1 and table 2. Table 1 has two columns and table 2 has only one column. So table 1 is supposed to be divided by table 2 to produce table 3. So table 1 and 2 both contains the P code column, and the second table doesn't have the customer code. So to be included in the table 3, the resultant column, a value of the unshared column customer code must be associated with every value of the P code, 3 values. So here the resultant table customer code, those customer code will be returned if that customer code is associated with all these P code values. This is our divide operation. Next, the last most parts are a little bit more concepts are still remaining. That's about data dictionary and system catalog. So databases store information about records, dependencies, access rights, ownership, etc. And these are all nothing but the metadata. So metadata are also stored as rows and columns of a table. So collection of this metadata stored in data dictionary or system catalog. System catalog accessed by TBMS to perform various transactions and data dictionary has the user accessible views that are accessed by the developers, designers and users. Then next, we should be familiar to all the relationships that are present in the relational database. So there are one-to-many, one-to-one, many-to-many. We have seen some sort of relationships in the entity relationship model also. These are mostly similar. So if you see, this is an example given to you, one-to-many relationship. A painter can paint multiple paintings using the crowfoot notation. It is being shown here. And let's say the similar thing you want to deploy in a table format. So see here, one painter num value 123. So the single instance has 3 instances in the painting table. So one value of painter num, one value is associated with multiple values of the painting entity. Likewise, another example explaining the same one-to-many relationship. Okay. So now I am going to move on to the one-to-one relationship. So in the one-to-one relationship, if you see, I'm going to enlarge it a little bit. So professor department. So single professor can chair one department. So there is a one-to-one relationship. So see here, through the department code, there is a column called department code. So through the department code, there is a one-to-many department. Okay, and it employs the professor relationship is implemented through the placement of department code foreign key in the professor table. So here the primary key in the department table is the department code, whereas here in the professor table it behaves as a foreign key. And see, each department code has a one-to-many relationship. And if you see through employee num, each employee num, the primary key of professor table is associated with single value of the department table, and that is nothing but your 1:1 relationship. If you compare each of the single data, you will also find this example in the book as well. So go through all the singles record values of EMP num and compare it with the EMP num with department. Next, the last one is our many-to-many relationship. So here, many-to-many relationship. So both of the entities have many-to-many connection in between them. So if you have many-to-many condition relationship like this, so there can be another one third entity which can be put in between those two entities which have many-to-many relationship. So one student can register to multiple courses in the enroll entity, and multiple enrollments can be performed in one class. So in one class. So enroll table's primary key will be the combination of foreign keys of class code student num, that is of the class code of the class and student num of the student entity. So that should be your middle entity in the many-to-many relationship. Okay, so that same example has been expanded in this format. Okay, and next, the data redundancy revisited. So here, what are we going to see? See, so data redundancy is something we always want to lower the redundancy in the database. In order to get an ideal database, we need to reduce the redundancy. So in the customer, we have customer code, and in invoice, we have invoice number. So customer code, there is one customer which is associated with there is a one-to-many relationship. So one customer code can have multiple customer code instances in the invoice entity. Okay, and here try to be careful about the data redundancy as well. In the same way, invoice connected to line and line again in terms connected to the product. So this is all in your relational database model. And let me show you something. Indexing example. So here see, the indexes are also important in database. Sometimes you need to keep track of the indexes. So indexing is used to optimize the performance of a database by minimizing the number of disk accesses required when a query is processed. So the index is a type of data structure which is used to locate and access the data in the database quickly. So how quickly it can determine? By this way. If you divide the database structure into multiple frames like this, so let's say you want to find out the department ID 1, so you don't have to go to this part or this part. Directly come here and start searching from the beginning to find out the matching one. Likewise, if you want to find out the department ID, so through the pointer or the index, go and find out the index value in the particular frame and find out the respective record that you want. Next, this is the most important concept, chords rules. So chords rules is a set of 13 rules. So here it's 7. After this slide, there are the rest of them, like 13 rules are there. So while designing a relational database, you have to obey all these rules, and this is set of rules called chords rules. It is used to determine if a DBMS can be considered a relational DBMS, that is RDBMS, or not. The guaranteed access rule here is that each item of data in a RDBMS is guaranteed to be logically accessible by resorting to a combination of table name, primary key value, and the column name. So all these things are supposed to be covered in the relational database in order to make it as an ideal relational database. So that's all in this chapter.